Okay, so for the next part of the course, we're going to look at hash functions as random oracles. So a random oracle is an abstract function that when you given a unique query, it returns a response, and you can't distinguish this response from a value which you drew uniformly random. You sample uniformly from a uniform distribution in its output domain. So it has to have three properties. In general, it should be unpredictable, as in like given the function, hash function, and its output, it's nearly impossible to predict another a hash function on a different value that will give the same output. So this is very similar to collision resistant, not collision, for second pre-image resistant. Sorry about that. So second pre-image resistant, and then it's you have the inversion resistant, which is essentially same as the pre-image resistance, and you also have collision resistant. So with these properties, in general, real world hash functions can approximate pseudo random behavior. Okay, but there are a few more caveats here that like it should not have in the snarks book, for example. These are the properties that are listed, but in general, I think unpredictability is a more stronger statement than just what is implied from here as second pre-image resistance, because it also means that there is no discernible structure of the hash. For example, if you have a hash function which is additively homomorphic, in general, it would not be a good pseudo-random function because you can predict structure out of it. So in general, it's very hard to have a true random function because it would have a description that is exponentially large. So what we have at best are pseudo-random functions. So how does it work in practice? So it works in the context of what is known as the random oracle model, in which hash functions or pseudo-random hash functions, which are cryptographically secure hash functions, which are good pseudo-random functions, act as the random oracle, as in they act as the source from which interactions between prover and verifier or multiple parties can get an output as a random value based on certain input. Okay, so in general, an interactive protocol works like this. So you have Alice and Bob, which are prover and verifier. So Alice sends a message, Bob responds with the symbol means we are drawing a value from a uniform distribution, and again, which is the challenge, and then Alice sends a message, Bob sends back a challenge, and so on. So in general, the goal is to find a way to simulate the generation of this thing so that we can avoid this interaction in a step-by-step way. So in a non-interactive function, this source of the uniform randomness is replaced by a hash function. Okay, and so Alice includes her message with whatever public input that Alice and Bob agrees, and then she chains her messages across with the public value and the previous randomness that she generates across her protocol. And then there is a one-time communication where Alice simply sends all the messages across to Bob. So in general, Bob can follow the exact same procedure. So he knows the public value. Okay, he has the set of messages, and then he can generate the randomness himself in the same fashion. So in this way, starting from a given setting, so generally these M1, M2 are the proof that's sent by Alice to Bob, and Bob generates the same randomness that Alice would have generated, and you have a consistent protocol. Okay, so this is the model where you turn an interactive protocol using the random oracle model to a non-interactive protocol where the generation of the random values is simulated using a hash function which acts as a pseudo-random function. Okay. So for this thing to work, both Alice and Bob also have to agree on the hash function, otherwise they would not produce the same randomness. So now we want to describe something concrete, which is the Fiat-Shamir heuristic. So the Fiat-Shamir transformation is what I sort of loosely described in a picture in the previous slide. It turns an interactive argument to a non-interactive argument in a random oracle model setting. Okay. So the verifier challenges in general in a multi-round protocol are obtained by hash chaining the prover messages. So here you have M1, M2 or the prover messages. So you hash chain them. Hash chaining essentially means that like the randomness of the first is input into the second one and so on. So each output is also further chained across to the next round. So this gives rise to what is called sequential binding between prover messages and challenges across the rounds. And the sequential binding makes prover accountable for every message. And generally, this means that the prover has no freedom to arbitrarily change messages M1, M2 at a later stage because of the avalanche effect. Suppose prover wants, after generating R3, if prover wants to go back and change M1, he has to regenerate all of them again, because once you changed M1, then R1 would change. That means R2 would change. That means R3 would change, and so on and so forth. So the challenges, so each round is in general bound to the previous round. Okay, this is sequential binding. And the challenges are unpredictable before one actually commits to the messages, which means before I send the message into the hash function, I don't know what the challenge is. Okay. Another thing is uniqueness. So this also ensures that a transcript or just a collection of messages that are sent in the protocol is unique, which means a given input or witness will always provide the same proof. A small change to prover message will affect all the challenges. So this makes the sequence of the proof uh, uh, in a way where the randomness is the same randomness that the prover will get, the verifier will also get, but it doesn't make that the proof itself to be deterministic. Okay. So that's uniqueness. Second thing, the third thing is that it's also is resistant to replay attacks. So a session identifier or a unique pseudo-random number generator for unique RNG seed for a given session is usually included in X. This means that like because you're going to produce the same randomness if you include the same witness, so you also have to include a differentiator across different runs. So each run of the protocol will also have a differentiator. In general, you include a timestamp or some RNG that differentiates. So you need to have replay resistance to replay attacks. Finally, you also need it to be non-malleable. Which means that somebody cannot take this a valid Fiat-Shamir transcript and transform it into another valid proof of some related statement. So it must be tied and bound to a given protocol and cannot be used somewhere else by just malleable, taking a valid Fiat-Shamir proof and then doing something to it. So in particular, the most common bug that is that like public values are not included in the hash chain, and or use a very weak hash. If you use the SHA-256 mod 32, that would be very bad. So mod 2.32, that would be very bad. So in general, one should use good collision resistant hashes and always include every public value for the protocol in the hash chain. So let's take a quick look at something, how to turn, for example, the Schnorr protocol, which is an interactive form, and then go to a non-interactive form. So Alice, for this, I'm going to sort of deviate from what we've been talking about and assume D log, discrete log. So Alice wants to convince Bob that she knows a secret W without revealing it. They agreed to use the Schnorr protocol for a D-log relation. So Alice and Bob agree on some generator G in some group. Okay. And Alice computes H, which is the discrete log of G, exponentiation of W with G, and sends this to Bob. So Bob needs to do few things, but before that, then Alice draws a random value from the multiplicative subgroup of G, and she computes what we call as the commitment to this value by computing the exponent of G with this random value, and she sends this value to Bob. So Bob is going to check first that these are not zero, which means in terms of these are elliptic curve points. So one needs to make sure that these points are not points at infinity, and then one needs to make sure that like these points are actually on the curve. So then Bob samples a random value from the multiplicative group and then sends it to Alice. And Alice computes the following object, and then she sends the value to Bob. So Bob has to check again that it's not a null value. And then if Bob manages to convince himself that A dot HE is equal to G power Z, then Bob knows that Alice knows the secret. And it's sort of easy to see because A is essentially GR. We plug this in here, and then we have the left hand side is GR, and H is G power W, so which essentially is G power R plus WE. And if this is equal to the right hand side, essentially then Bob is convinced that Alice knows W. Note that Bob does not know about W. Bob only knows that Alice knows W. So this is not revealing the secret as promised. So now how does this work in a non-interactive setting? We do exactly the same thing, only that like wherever we sampled a value randomly, we're going to simulate it with a hash function with a small caveat. So let's again start with Alice and Bob. So Alice starts with this same way that like note that like here she sampled a random value here, and I'm going to explain to you in a short moment as to why I'm not using a hash function for this. So then Alice computes the commitment of this random value with G, and then the note that like the value that Bob samples, which is the interaction, is essentially replaced by the hash function. And the hash functions includes all the public values, which is G, this is Q, and all the values that Alice sends to Bob, which is H and A. And Alice computes the Z and then sends it to Bob. Okay. Now, why should you not use the hash function to compute R? Because the purpose of R here is essentially to hide the value of W. Okay. So R is not something that should be derived. In fact, Bob does not know about R at all. Bob does not know R, and that's really important that it stays that way. So whatever random value is sent by Bob is exactly that should be simulated by a FHML hash. So in principle, in general, R you could use some commercial pseudo-random number generator, but not from the FHML hash. So then the interaction essentially goes in the same way. This time just Alice sends Z, A, and H, and Bob does the simulation of the interaction, by computing the hash in exactly the same way that Alice computed. And then if he's convinced, then if he finds that the left hand side and the right hand side are the same, then he's convinced. And this is the non-interactive version. So for this non-interactive version to work, Alice and Bob have to agree on the hash, how they are including the public parameters into the hash, and apart from everything that is needed for the Schnorr protocol to make sense. Okay, so that's the definition or application of FHMIR in a specific example. Now we are going to discuss a specific construction called as the spongefish construction, which is a very more recent development in the literature, which uses sponge hashes for defining FHMIR. So far, what we saw was hash invocations. Every time one needs to hash a message and generate a challenge, we call a separate hash function. In principle, you could replace this with a sponge function with certain properties, and that's what we're going to discuss here. So spongefish uses a stateful hash, stateful sponge hash in an overwrite mode for FHMA transformation. So we saw earlier a functionality for a sponge, and I'll use the same picture here for clarity. So the yellow blobs are the ones that you write, and the green blobs are the ones that you read. And the red part is the capacity, or what we also saw in the SHA-256 example before. So the red part is the private part, as in like it's a sponge's internal state. It's not accessible by prover or verifier or anybody. So when you initialize the hash, you initialize it with some zero values, some initialization vector in the rate and capacity. But whenever in a protocol a prover needs to send a message, he is able to write to the rate part, and the rate part continues to accept messages until it saturates its size. And once it saturates its size, it triggers a permutation function, which then changes the state of the hash. Okay, and then when it wants to read, or when you want to get a challenge, for example, you can read from the state of the hash again until you reach the rate index. Once you saturated the rate size, then a permute function is triggered. So if you want to read 2 R bytes, you read R bytes first, permute, get the result, and then read another R bytes. Okay, so in general, the sponge has 3 functionalities: absorb, squeeze, and ratchet. Ratchet essentially takes a given state, it actually applies a permutation first, and then it zeros the rate part. Okay, so we'll explain why it's useful. So basically, there is a read write rate part and an internal state called a capacity part, which is private to the hash. Now note that hash chaining is always maintained in the sponge, in the internal state of the sponge, and there's no need for multiple hash invocations because the capacity part is kept internally chained by the hash. So if you put some initialization vector, and then once you apply a permutation, you have no way of recovering it back by inverting this permutation, if the permutation is a secure function like SHA-256, for example, or SHA-3. So we do need to use a cryptographically secure permutation function for the sponge. And in general, the hash's statefulness allows it to chain the hash without recalling the hash function again and again. So so you can think about a sponge as a wrapper on the hash permutation, which is the mathematical algorithm which takes a state size n, permutes, and returns a state size n. Okay, so this is a good definition to keep in mind. So let's look a little bit closer at the absorb function. So as we said before, the absorb function can write to the rate part up to R bytes at a time. So each time the rate part is saturated, a permutation function is triggered. An important thing is all the metadata in a protocol, such as labels, sizes of vectors, etc., are supposed to be encoded in the initialization vector in the instantiation of the hash. We will define an example, we'll show an example of how you do that. And the only data that is absorbed by the sponge is the actual data generated by the prover. So for example, if you are looking at the Schnorr protocol, there may be some metadata such as labels. We don't need to include them at every time we send a value for absorb in the hash. What we do is that we include all the metadata in the beginning of the hash in the initialization value, and what we actually include in the sponge at any given time is the actual data generated by the prover. Okay, so one important thing here is about override mode. So now here, suppose if you have more data that is appearing, like you have some state, right? Here you have 0, and then we have a data that is written into the rate part. The override mode does not XOR the data, or if the data is field elements, it does not do modular arithmetic. It simply overwrites them, and this is shown to be secure in this paper. So in the overwrite mode is also efficient, because then you don't need to do unnecessary XOR operations. And anyway, you have no control over the full state of the hash. You can only read or write with the rate part, so it does not affect the security if you keep a sufficiently large capacity part of the hash. So the next operations are the squeeze and ratchet. They also work in exactly the same way. So we can read from the rate part up to r bytes at a time, and once you read r bytes, we always trigger a permute function. It makes it easy to generate multiple challenges. So you just need to keep, for example, if you are taking r by 2 bytes, then multiple challenges would not require you to do permute function. Just simply do r by 2 and r by 2. And ratchet in general is allows you to state clear. In general, it's useful for forward secrecy or protocols that require state erasure and so on. So now what we want to do is to like sort of spend some time on how do you initialize the sponge, like how do you define the initialization vector. The idea is that, like, for a given protocol, you have a sequence of actions. Like in the Schnorr protocol, the prover has to do some prescribed actions according to protocol, and the verifier has to do a prescribed set of actions according to the protocol. Now, the sequence of operations you can think about as talking to this random oracle. So every data that is sent to the random oracle is an absorb, and every data that is required from the oracle is a squeeze. Okay, so you can format the sequence of operation in a domain separator string. So here, for example, I have just laid out the sequence of operations in the Schnorr protocol for the prover. And as we spoke before, not every bunch of data that is randomness that is used in the protocol is generated from Fiat-Chamere. For example, randomness that is meant for zero knowledge should be generated from a pseudo random number generator, which is private to the prover, okay, and not something that is shared by prover and verifier using some common definition. So let's just look at an example of the sequence and how we encode it in some domain separator function. Let's define it with some label, say spongefish, and we define some method for adding the points. So the first method is to add the h, or rather the g. Then you add the public key, which is h, right? And then you add the scalar q. You see, note that this is exactly the sequence of the hash function, okay? And then you ratchet, which is some state clearing thing for basic security. And then you add the commitment, which is a here, okay? And then finally, when you want to generate the challenge, you call the squeeze operation. you define some function challenge scalars, and finally you also want a response, which is z, right? So every data that you generate in general is always added to the sponge. So you add the data that is generated by the, and this is basically a sequence of operations. Okay, so I have not, note that I have not put the actual data here. So I have only encoded the sequence of operations in a string. Okay. So this, for example, generates a string of this format in Spongefish. So where I'm not yet doing any hashing, I'm defining an initial value. And in the initial value, I've encoded the form of the Schnorr protocol or the sequence of the Schnorr protocol as a formatted string with some specific prescription. Here the A stands for absorb, and R stands for ratchet, and S stands for squeeze. Okay, so the formatting here is that, like, for a given operation you have an operator indicator, then you have the size. Here it's like 32 bytes, so I put 32, and then you have the metadata, which is the label. Okay, so generally speaking, you have a padding like this where you have the operation, then you have the size, and then you have the metadata. Okay, so you encode it with null bytes, separated by null bytes, in a formatted string. So in principle, for long protocols, you could write some constructor for doing this thing. And protocols which have repetitive structure, like round by round protocols, will have absorb, squeeze, absorb, squeeze, absorb, squeeze, something like that. So you can encode all of them as the string. And what it does is that it fixes the exact set of operations that you can do and encoded it as a initialization vector for the protocol. So whoever is running this protocol essentially must start with this initialization vector, and perhaps also add some pseudo randomness for the session uniqueness. Okay, so given a domain separator string, for like what we saw before, the spawn state is essentially initialized by initial value. You essentially hash this thing with whatever hash you are using to 32 bytes. Okay. If you have size, which is for some reason the domain separator string is larger than 32 bytes, then you sponge it until you get to 32 bytes. And then your initial state is an encoding of the exact protocol sequence that you are working with. So if you are in a fry protocol and you have n rounds, so you will have absorb sequence, absorb, squeeze, absorb, squeeze, absorb, squeeze as many times as it's needed in the protocol. Okay, with the corresponding messages as well. So you encoded not only the sequence of operations, the size of operation, and the metadata as well. So now the functionality of Spongefish is that given this domain separator string, it's sort of, there's a parsing method that simply parses it and determines the opcodes that the sponge will execute. And this is really nice because given a protocol, you have fixed the sequence of operations and the exact set of operations. So if I have a Schnorr protocol, then the prover and verifier are essentially allowed to do this exact set of operations, and any deviation from this would terminate the protocol because there is some kind of malicious operation. Okay, so that's pretty nice structure, and also makes it easy for people to write or use fiat shamir without going too deep into all these constructions. So the sponge wrapper plus a formatted domain separator string makes it very clear exactly what you need to do. And because the hash is stateful, you have only the absorb, squeeze, and ratchet methods. All of them only affect the rate part, and the capacity part is private and internal to the sponge. So every metadata, such as these labels, are only going at the initial stage in the initialization vector, and then in runtime you only send in the actual messages, which is actually very good for on device, like running it in a GPU or I don't know, some other device, because in general you don't want to keep anything which is not generated by the prover. If you have some metadata, then you have to find some place to store it and keep moving, and all of it is it's very clean in terms of this construction. An important thing is that setting the initialization value to be this formatted string ensures that both prover and verifier can start from the same state, and then the sequence of operation remains deterministic. Okay. To summarize, we need to use a collision resistant hash function such as SHA, Ketchak, Blake, or Poseidon. And the domain separator has to have certain properties. So first thing is that it must be unique and deterministic for protocol. So each protocol must use a unique formatted domain separator to prevent cross-protocol attacks. So this null byte, no null bytes is because of the specific pattern used by Spongefish. It's not necessarily something generic in Fairchamir. And the public data must be included in domain separator definition as well. And the transcript must be consistent in general, right? And one particular way in which you can ensure transcript consistency is the operator order enforcement, as in the sequence of absorb and squeeze operations. And this you essentially ensure by defining your domain separator string well. And you have to implement some functionality which Spongefish does, which ensures that the sponge only operates in that sequence. So any deviation from this must result in an error. So all prover messages must be included in absorb, since most protocols that we use for snarks or starks, or let's say any cryptographic protocol that we use, we know the sequence of steps that need to be taken. In general, it's deterministic in the sequence of steps. So one can implement this operator order and ordering enforcement directly from the protocol knowledge of the protocol. The other important thing is whenever there is a need for ZK or zero knowledge, then prover needs to maintain a private pseudo random number generator, which can be kept in sync with the protocol, but this is something that the verifier would not be able to access. If there is protocol that needs state erasure at critical junctures like ratchet, operation can be used. And in particular, prover state is kept non-clonable because you don't want to reveal the sponge private state. So this can prevent leakage or accidental leakage of private randomness and so on. So we don't want that. So I think that like we have covered most of the practical things related to Fiatchamir, and I think that will be the end of this lesson. So here are some references that you can take a look at. I also encourage you to look at the exercises, and there are various references on Fiatchamir. There's also some interesting articles by Trail of Bits. I encourage you to look at that as well. So thank you.